So the problem, so let's talk about that problem on the homework that that caused a lot of you a lot of grief. So I think it was something about, there was something orbiting something, right? It was was satellite in the Earth. Okay, so we have the Earth and a satellite. It's orbiting at some given distance. Is that what it was? Some given distance. So, and part one was just find its speed, right? Yeah. And a lot of people could actually do that, and it said use the momentum principle, in fact, didn't it? I think it said use the momentum principle. So which version of the momentum principle do you want to use here? Find its speed. Well, do you have 2 times? Not really. So we better use dp dt equals f net. Yeah. No. This is a perfectly legitimate. This is a perfectly legitimate statement of the momentum principle. You could also write delta p as f net delta t, and that would be good too. Okay. And then, so where's, so we're looking for speed, I think. So speed is the unknown. It's going around in a circular orbit, presumably at constant speed. Well, so where's Waldo? Is the speed going to be over here? Definitely not. That's the gravitational force. So it better be in here, hadn't it? And so we can analyze these two things separately. This is going to be equal to a minus g mass of the Earth, mass of the satellite, over r squared, r hat. It's a force, right? Yeah. And what do we know about evaluating dp dt for curving motion? So there's no parallel. If it's circular at constant speed, if it's not speeding up or slowing down, the force is just turning the momentum, right? So the force, if it's here, there's a force turning here's the momentum, there's a force turning the momentum. There's no parallel component speeding it up or slowing it down, right? So then we have an expression for the perpendicular component. So we have, correctly you say we need to divide it into dp dt perpendicular and dp dt parallel. That one's 0, so we have pv over r, and it looks like we can get a v out of here, right? Yeah. So we get a v. So we get a speed, and most people could get a speed. We okay on that piece? Okay, so then the question was, how much work would you or a space tug or somebody have to do to take the satellite out of this orbit and move it really far away where it still had some final non-zero kinetic energy? Is that what it was, or? Oh, it said the minimum amount of work that you needed to do to move it really far away from the Earth. So the minimum would be you get it really, 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 really far away, but it's not moving. So, well, that sounds like 2 different distances, doesn't it? So that sounds like 3, the energy principle, doesn't it? So let's see what we can do with the energy principle, given that we now know its speed. So it helps to draw a picture. So here's our initial state, and our final state is here's the Earth, and here's the satellite way over here, not moving. And this distance is basically infinite, really big, really big. So now we write down E final is E initial plus work. What's the unknown? Work. That's our unknown. So there it is. What are we going to choose as the system? The satellite plus the Earth suggests itself as a good system, doesn't it? So system, satellite plus Earth. Okay, so we have initial state. We got some kinetic energy, right? Satellite has kinetic energy. We can be in a reference frame where we're at rest with respect to the Earth, so we can say the Earth's kinetic energy is zero. We can write it down anyway. And what else goes in the initial state given our choice of system? Okay, potential energy, so the gravitational potential energy. And we can put the rest energies in, mass of the Earth, c squared, mass of the satellite, c squared. That's pretty comprehensive, plus work. And we pretty much have all the same terms on the other side except not the work, right? So we have final kinetic energy of the satellite, final kinetic energy of the Earth, final gravitational potential energy, final rest energy of the Earth, rest energy of the satellite, and these are all final. So that looks like the equation, doesn't it? And now the next thing we do is, so this is what I expect to see when you work these problems. The next thing we do is say, is there anything that doesn't change? Okay, the rest energies don't change, so we can just say no change. I'm just writing no delta as a shorthand. The test goes through 6.4, I think, which is work but not potential energy. So, kinetic energy of the Earth probably doesn't change much either. So, no change, no change. So we're down to a much simpler looking equation. Final kinetic energy of the satellite plus the final gravitational potential energy of the system is equal to the initial kinetic energy of the satellite plus the initial gravitational potential energy plus work. Now, are any of these things zero? Okay, so this is at rest, so this is, and the final gravitational potential energy. What's the equation for gravitational potential energy? Okay, so we have the gravitational potential energy was a minus G M1 M2 over R. And here, so we have a minus G M over infinity, basically, or something really big. And so that number is close to zero, isn't it? Yeah, it's zero. So that's zero. So it looks like everything on the left is actually zero. The final energy of the system, except for the rest energies, is zero. So we've got, this side's going to be zero. Initial kinetic energy of the satellite, well, we know its speed. We just figured that out in the first part, right? So we have a half mass of the satellite, v squared, where that came from part one. And what's the gravitational potential energy? This minus G M over whatever that distance was. And we have a plus work. And so we should just be able to calculate that and calculate that. We know all those numbers and get the work. Yeah? So what happened? Why was that last step so hard? So thinking about what the final, really thinking about what the final state was. No, what was it? Calculation errors. Okay? So that's a nice problem because you get to use both principles. A little large for a test problem, but... So questions about this?